Okay, guys, today we're going to talk about transformations. Um, I always do transformations after the quadratic forms because, once we get into this, one of the forms is going to kind of appear. It's going to look familiar to us. I always wait until we get vertex form before I do transformations. This one's a lot of writing, so I wrote this down for it. I wrote a lot of it down already. The blank copy of this, so again, I have a lot of the outline already done. The blank copy of this is in Google Classrooms if you need it, if you don't want to write everything. Or you can just, pause and write what I have already written down. Alright, so transformations are changes to the position or size of graphs. Okay, so we've graphed a lot of things so far, and we've noticed that not all graphs look the same. They look similar to each other, but they don't look identical. Some start in different places, some end in different places. Some are bigger, some are smaller, skinnier, fatter. We've seen a bunch of different things. Okay, those were all due to transformations. There are three types of transformations: translations, dilations, and reflections. Okay. Translations are also called shifts. Okay. What translations do is they move the graphs up, down, left, or right. Okay, or shift the graphs up, down, left, right. Okay. Now you could have multiple translations in each graph. Okay, now obviously you can't move left and right at the same time, but you can move up and to the left or up and to the right. So there could be multiple translations on each of these. Okay. The second one up is dilations. What dilations do is they make a graph wider or narrower, or skinnier or fatter if you want less mathematical terms. So makes the graph wider or narrower. Now the words we're going to use for this, instead of wider or narrower, we're going to say if it's a stretch or a compress. Okay. Now there's two types of dilations. There's vertical and horizontal. In Algebra 1, we're only going to deal with vertical dilations. But just know that there are two different kinds. And then reflections. Reflections change the position of a graph over a line. They reflect over a line. So the ones we deal with are we could reflect over the x-axis. We could see reflections over the y-axis. And the one we're not going to do is you could reflect over a line. Like sometimes there's reflections over the line y equals x. Alright, so those are the three: translations, dilations, and reflections. Three types of transformations. Alright, so before we actually start to transform functions, we need to talk about parent functions. Okay. And we've dealt with parent functions a little bit. Whenever we introduced a new function, linear, quadratic, exponential, we talked about the parent function. The parent function being the most basic form of function type. Okay. So all quadratics are built off the parent function quadratic. All linears are built off the parent function of linears. Okay, and they all look the same, kind of like, a lot of kids look like their parents. Same thing here. A lot of graphs look like their parent graphs. Okay. All right, so the families. We're going to do 7 families. There's 12 main ones. We only deal with 4 of them in Algebra 1, but we're gonna do a couple more. First up is the constant family. Okay. And for each of these, we're going to talk about the equation, the graph, the domain, the range, and then an important point, kind of the main point that we focus on. So the equation of a constant function is just f of x equals c. Okay, where c is just a number. So there's no variable in there, there's no x value, it's just a number. F of x equals a number, or y equals a number. Okay. The graph of a constant, okay, well, if you just have y equals a number, we already know that from, way back at the beginning of the year. Y equals a number, and there's no other variable in there. That's just a horizontal line. There's only a y value, it's a horizontal line. So constant functions are just horizontal lines. Okay. At some number c. Okay. So again, obviously that's at 3, but it could apply to any number c. The domain of almost every function that we deal with is all real numbers. Okay. And it's no different for this. You could plug in any x value, and it doesn't matter because there's no input. So it's just any x value. As far to the left as you could go, as far to the right as you could go. The range of a constant is a little different than our normal ranges. Remember, range is all the y values. Well, there's only one y value, and it's c. So your range is just c, whatever number c is. And then an important point. Okay, now all these points are going to have the same y value. So how do we pick an important one? We're just going to use the y-intercept. For a lot of these, we're going to use the y-intercept. Okay. So the y-intercept of a constant graph is just 0, comma, c. And again, whatever c is. All right, so that's the constant family. All constant graphs are going to look like that. Now again, they might be, it might be down here, might be up here. There's different versions of it, and it shifts up and down. All right, linear family. We already dealt with linears. Okay. The most basic form of a linear function is f of x equals x. Now again, remember, f of x could be y. You could always write it as y, so the constant could be y equals c. Okay. The linear graph is the equation y equals x. Okay. Or in function notation, f of x equals x. Well, we know what that graph looks like. It doesn't have a y-intercept, and has a slope of 1. Oh, this graph got shifted. Oh well. So it goes through the main diagonal with a slope of 1. Okay. And again, we know from the linear unit that the domain of a linear function is all real numbers, and the range of a linear function is also all real numbers. Okay. So you go as far left as you want, as far right as you want, as far down, and as far up, and there's going to be a point somewhere. All right, now the important point for a linear function is going to be the origin, 0, 0. Now again, that important point is how we're going to transform these functions. Like we'll take that important point and we'll move it up left, or we'll stretch it by 2. And we'll talk about that more in the next part. All right, quadratics. It's what we're currently in. The parent function for a quadratic is f of x equals x squared. So remember, in standard form, your a value is 1, your b value is 0, your c value is 0. It's the most basic quadratic you could have. Again, or y equals x squared. The graph of this, we know it's a parabola. It's a vertex at 0, 0, 1, 1, over 2, up 4. And you reflect it over. And then draw your line. All right, domain. I've already talked about domain is all real numbers again. You could plug in any x value, and you'll get a number out. The range isn't all real numbers. Okay. The range depends on the min or the max. It depends on if it opens up or down. So the range on this is that you'll notice that none of the values are lower than 0. No y values are less than the origin. There's nothing down below the x-axis. So your range is all y values are greater than or equal to 0. And then the important point on this one again is going to be the origin, 0, 0. All right, then if you remember from third quarter, we did exponential functions. Okay. The most basic exponential function that we had was f of x equals 2 to the x power. Okay, so remember, exponentials are when you have a variable in the exponent. Okay. The graph of this went through the point 0, 1, because if you plug in 0 for x, you get 2 to the 0 power, which is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the negative first is a half, and a quarter for negative 2. All right, so remember, they start really slow, and then they increase rapidly. So again, all exponential functions are going to look like that. All quadratics are going to look like a parabola. Again, it's apparent, it's the most basic form of each of these functions. All right, domain and range. The domain is all real numbers again. The range, now again, similar to the quadratic parent function, there's no values down here below the x-axis. Okay. Now, if you remember from exponentials, though, remember that it never actually touches 0. It's called an asymptote there. So we can't make it like a quadratic where y is greater than or equal to 0. We have to just say that y is going to be greater than 0. Because remember, it's never going to get to 0. You could plug in negative 1,000 and you're not going to get 0. You're going to get a very small number, but it won't be 0. All right, and then the point for an exponential is going to be the y-intercept. Now again, the y-intercept on this isn't the origin. It's the point 0, 1. All right, now those 4 are all the algebra 1 functions that we deal with. We're going to do a couple others just to show them, introduce them. First one being the cubic function. Okay. The cubic function is the next power function. So we have linears, which are x to the first powers. We have quadratics, which are x to the second powers. And now we have cubics, which are x to the third powers. So the equation for a cubic is f of x equals x to the third. Again, I'm just introducing these. We're not going to do a whole lot with them. Maybe graph them, maybe translate them. The graph, again, if you need points for a graph, you just plug in x values. Plug in 0 for x. 0 to the third power is 0. Plug in 1 for x. 1 to the third power is 1. If you plug in 2 for x, 2 to the third power is 8. Way up here. Okay. So cubics look a little weird. If you plug in negative 1 times negative 1 times negative 1 is negative 1. And negative 2 to the third power is negative 8. Okay. So this is kind of a strange looking graph, one we're not too familiar with, or not familiar with at all. It's kind of like this S shape. Okay. That's not a very good one, but I'm going to leave it. So cubics get really big positive values and they get really small negative values. All right, the domain is all real numbers. So we're going to run through these kind of quick because we're not going to do a whole lot with them. The range goes all the way down. There's an arrow pointing down and there's an arrow pointing up. So that means it's going to cover the entire range, every y value from negative infinity to positive infinity. And then the point we're going to use is the origin 0, 0. Next up is the square root parent function. We did square roots when we did radicals and exponentials. A square root function is just f of x equals the square root of x. Or again, y equals the square root of x. Now the graph of a square root's special. It's different from all the other ones. The square root graph, okay, if you remember from our radical unit, we said you can't have negative numbers underneath a square root. Okay, because nothing times itself is going to give you a negative. So you can't have -1, you can't have -2. Okay, the square root of -1 doesn't exist in the real numbers. The square root of -2 doesn't exist in the real numbers. The first thing that does exist is 0. The square root of 0 is 0. Okay. And the square root of 1, again, you're trying to think what times itself is 1. Well, it's 1. So 1, 1. Okay. If you go over 2, you're trying to find what times itself equals 2. Okay. Well, that's not an even number. We don't know. It's not even a rational number. Same thing with 3. Square root of 3, what times itself is 3? I don't know. The next one we can do is 4. What times itself equals 4? Well, it's 2. So 4, 2 is a point. Okay. So the only nice points on these are going to be perfect squares. Okay. If you go over 9, you would have to go up 3, because 3 times 3 is 9. So this is kind of like it's a partial sideways parabola. So it looks like that. All right, now the domain is all the possible x values. Okay. Well, we said we can't have negative x values. So the domain this is the first one that's not all real numbers. Okay. You can't have negative x values, and the first x value we can have is 0. So that means all of our x values have to be greater than or equal to 0. And then you can tell from the graph, all of our range values are also going to be, they're all above the x-axis, and they're all right of the y-axis. Let me change the colors here to keep so x is greater than or equal to 0, and y is also greater than or equal to 0. So it's everything in the first quadrant. All right, and the important point for that is going to be 0, 0 again. All right, and the last one is one we did deal with, but we dealt with it as an equation, not as a graph. It's the absolute value function. The absolute value function, the equation, the parent function is f of x equals the absolute value of x. So remember, absolute value, vertical bars, or y equals the absolute value of x. If you recall what absolute value is, it's the distance away from 0. It's a positive distance away from 0 because distances are always positive. So our graph is only going to have positive numbers. Okay. The graph of an absolute value is a V shape. Okay. The parent function graph, the positive ones, positive x values have a positive 1 slope, and the negative x values have a negative 1 slope. So it's the main diagonal of the V shape. Which is why I always tell you your quadratic graphs can't be V-shaped, because V-shaped is already taken. They have to be U. It has to be parabola. Domain is all real numbers. You can plug in positives, you can plug in negatives. Switching these colors. The range, you could tell from the graph, is it's never going to be negative. Okay. There's no negative values. There's nothing below the x-axis. So the range is going to be all y values greater than or equal to 0. And our point, we're going to use the origin 0, 0. All right, so those are our 7 parent functions that we're dealing with. Again, absolute value, square root, cubic. We're not going to do anything with their equations. We might only deal with their graphs. But then exponential, quadratic, linear, constant, we've already dealt with. Okay, so you might have to work with their equations a little bit more. All right, so those are the most basic parent functions, most basic form of each function. All constants are going to look like that. All linears are going to look like that. All quadratics, all exponentials, they're all going to look like their parents. Okay. All All right, in the next part, we'll actually do some transformations and see what happens with those. All right, have a great day.